Hello, everyone. Welcome to the lecture Internet of Things. I'm Neda, and today I'm going to talk about digital communication protocols. Okay, let's start. We'll learn what is microcontroller, more especially RP PicoW, its specifications, and its pinout diagram. As we see in RP PicoW pinout diagram, there are GPIOs can play the role of I2C, SPI, and UART. These communication protocols are popular in the world of electronics and often used to enable transfer between microcontrollers, sensors, and other peripherals like actuators and displays. Each protocol has its unique features that make them suitable for different types of data communication. Based on the required speed, complexity, and the number of devices involved. As you can see here, this is a question that how we can communicate with all sorts of different sensors, actuators, and displays. And the answer is using digital communication protocols, I2C, SPI, and UART. Maybe someone asks, there is a MicroPython library that we can use where someone's already converted the low-level function into an easy-to-use interface, and we should say no, because there are a couple of standard ways of connecting low-level digital devices together that are implemented in MicroPython. It means that they are built in the firmware. When we do firmware updater, this functionality, I2C, SPI, and UART exist. It's not like that we go and or someone else write the library for them. Okay, let's see what is I2C and SPI. First of all, I'm talking about these two protocols, and then I will talk about UART. I2C, as the name shows, it's inter-integrated 2I, I2C circuit, and SPI serial peripheral interface protocols. This is the similarities between these two. I2C and SPI are called input-output protocols, and I2C and SPI define a way of wiring up a two-way interface between two devices. Many parts come in versions with either interface, so we can pick the one that's right for our project. It depends what is our project, and then we can choose which one we are going to use. Also, it depends to the sensors. The device that Pico is supposed to connect to it. Later, we will learn how to use these protocols. In both cases, there is one device that controls the communication. It means the PicoW, and one or more that waits for instruction from the main device. And there are a few differences. To demonstrate the protocols, I choose a serial LCD module, and this module has both I2C and SPI interfaces. That belongs to SparkFun, and I choose it because I want to show the differences between these two methods clearly with the same hardware. So we can see easily the differences. I2C inter-integrated circuit. In this I2C protocol, communication plays on two wires. A clock that's usually marked as SCL, it means serial clock, and a data channel that usually marked STA. There are two I2C buses. If you look at the Pico pinout diagram, there is I2C 0 and I2C 1, but many of them. They are I2C 0 and I2C 1, they are the types. And we have two types, 0 and 1, but there are many of them when you look at the Pico PW diagram, and we can use either one of them or both of them. In the following example that I'm gonna show you, we use I2C 0, that is GPIO 0 for SCA and GPIO 1 for SCL. Wiring I2C is just a case of connecting the SCA pin on the PicoW with the SCA pin on the LCD, and the same for the SCL. Because of the way I2C handles communication, there are also needs to be a resistor connecting SCA to 3.3 volt and SCL to 3.3 volt pull-up resistor, and typically these are about 4.7 kilo ohm. I2C is commonly found in applications that require communication between multiple low-speed peripherals and the center processor. Okay, here is a wiring of a SER LCD module for I2C. In this, if we use SER LCD device, we don't need resistor because they are already included in the device, and we call it built-in resistor here. And we don't need to add any extra one to our circuit. We have, if you look at here, this is written CL, that is clock, and DA, that is data. And this is the power that goes to the V-bus that I mentioned before. And this is powered from the USB, and this is 5 volt. And this is also this black wire, it goes to the ground. So we can see here that is called GPIO 0. It goes to our data pin in the LCD, and GPIO 1 that goes to the clock. Overall, with the power and ground, we have 4 wires in the I2C connection. This code snippet shows you how to connect PicoW to the I2C device and send the data. I will explain it in MicroPython section by detail, but you can see that here we are defining STA with as a pin 0 of the machine, and machine is a library that we are using it to connect, to work with connection our Pico to the LCD. And SCL is connected to pin 1. We saw in the previous picture here. Exactly, we are defining these two, GPIO 0 and GPIO 1. After defining these two, I2C is defined like machine.I2C with these parameters. STA as a STA is defined as STA, and this STA is exactly this one that we define, and SCL is defined as a SCL, and this SCL is exactly this line. And with frequency with 400,000 megahertz. So we can write to through I2C to the module, and we can show the character on that. This is the address of the device, and we will write hello world on the, we will see the hello world on the LCD module. Okay, what is the next is SPI, Serial Peripheral Interface. SPI utilizes a full duplex machine master-slave architecture, and when we say full duplex, we have half duplex and we have full duplex. Full duplex means that at the same times you can send and receive, and half duplex means that when you are sending, you cannot. It's one way is working at the same time. You cannot send and receive. So SPI has 4 connections: serial clock, MOSI, MISO, and CS. And sometimes we label it SS. In SPI terminology, you will find what this abbreviation are. Serial clock is the clock, and MOSI is the line taking data from your PicoW to the peripheral device, that in this case is LCD, and MISO takes data from your peripheral device to your PicoW. CS stands for chip select and is used to connect many devices to a single SPI bus. You simply have to apply power to the CS line to enable an SPI peripheral and pull it low to disable it. I will tell you why you should pull it low, because there is a not C, not CS, and I will explain you. Also, we can connect the CS to a GPIO pin and toggle it on and off to enable and disable the display. But since we only have one device in this demo, we can simply connect it to the ground to keep it enabled. And SPI is used in applications such as SD cards, sensors, and displays. This is the SPI terminology, and if you see here, we have MOSI, master out, slave in, and master in, slave out as MISO. And it means that we have 2 data wires, and data can travel in both directions at the same time. So you can read more about this SPI terminology. Okay, how we wire up a serial LCD module for SPI. Here you can see the power is connected to the VBus or Pico VBus pin, and the ground is connected to the ground. And you can see except from these 2 wires, we have 4 wires. So one is STO, that is data, and connected to Pico MISO. Here we have the data. This is the, let me see here. This is the SCK. This is a clock, goes here. And this is the STO, that is the data, and goes to this pin of the Pico, and this is the GP4. And the next one is STI, that goes to the GP3, 0, 1, 2, 3, and this is the ground, 0, 1, 2, 3, and 4. Be careful about this Pico diagram. You should know about it. This is 0, this is 1, this is ground, 2, 3, and 4, as is mentioned here, exactly like here. And the last one is not we should read this /CS as a not CS. It means that it's opposite of CS. You need to bring it low to enable the LCD and high to disable it. There is no CS that we say that, okay, if I put it high, it will be activate, and if I put it low, it will be deactivate. It is here is inverse. By putting make it low, it will be enable, and put it high voltage, it will be disable. So let's see how this code snippet works and connect our Pico to the SPI device and send data. SPI clock is defined in pin 2, as we see here. This is the clock and goes to pin 2, 0, 1, ground, 2. SPI TX is connected to pin 3, and SPI RX is connected to pin 4. And this SPI is defined by these parameters, and this is the ID and baud rate of 100,000, and the clock as a SPI clock that defined here, and mostly as a SPI TX we define here, and MISO as a SPI RX and we define here. And as you can see, there is no device address in SPI. We don't need to address it. If you compare it with the code for the I2C that we had the address, here in SPI we don't need. Okay, but what is baud rate? As we define here as the baud rate or frequency in our code, let's see what is it. Most types of serial communication protocols such as I2C and SPI have a speed or baud rate, which is basically how many bits of data it can push through the channel per second. Baud rate is affected by many things. Capabilities of the two devices being that are connected, and the wiring between two devices, such as how long is the wire, and if there is inferences from other devices. And if you find you are having problems with mangled data, then you may need to reduce baud rate. And fine-tuning baud rate does not matter when we are sending 1 byte data per character to LCD, but for some other SPI devices, such as pixel-based displays, fine-tuning the baud rate can be important. And the last digital communication protocol is UART. It's abbreviation of Universal Asynchronous Receiver Transmitter. UART is a simple and widely used protocol that enables serial communication between devices. At the physical level, UART consists of two lines, RX and TX. RX is receiver and TX is transmitter. UART does not require a clock signal, and the unit of communication is a character, not to be confused with a string character that here it can be 8 or 9 bits wide. And UART is typically used for communication between microcontrollers, computers, or other devices over long distance. But the difference between UART and I2C is that I2C is a bus and we can connect many devices to this bus, but UART is a peer-to-peer device. Only two devices can be connected to each other. So let's see how we set up a UART. First of all, you should create a UART object of the given ID and baud rate. Here, you created UART with the ID and baud rate. And as it's mentioned here, there are constructor, and you have you can create UART based on this constructor. So after creating an UART, we should initialize it and initialize the UART bus with the given parameters. These parameters are explained here. Baud rate is the clock rate here, and bits is the number of bits per character. It can be 7, 8, or 9. And here in this example is 8. And parity is the parity, non-zero or 1 odd. When we say 0, it is even, parity even, and when we say 1, it is parity odd. And stop is the number of stop bits, and it can be 1 or 2. And here in this example is 1. Okay, this is how we should set up an UART. But how we read UART reading, and how we do reading and writing in UART. A UART object acts like a stream object, and reading and writing are done using the standard stream methods. For example, here UART.read read 10 characters and returns a byte object. UART.read read all available characters. There is UART.read line and read a line, and UART.read info into buffer. It means buffer. Read and store into the given buffer. And UART.write ABC write the 3 characters. You can find more information about the UART in this link. About all others methods and or other function, more information about the UART if you need. There is a concept is called Bitbanging. RP Pico W has 2 hardware I2C buses and 2 hardware SPI buses, as we mentioned. But you can use more than this if you want to. How? Both I2C and SPI can be implemented in software rather than hardware. This means the main processing core handles the communication protocol rather than a specialized hardware piece of the microcontroller. This is known as bitbanging. Bitbanging, as it can be useful, it puts more strain on your processor core than using specialized hardware. And you may find that you can't reach high baud rate. So it was all about digital communication protocols, and thanks for your time. And if you have question, please write me on a Slack and on the group, channel group. Goodbye.